size of the atom or ion. The ionization potential of an atom is inversely proportional to the atomic size. So greater will be the atomic size, lesser will be the attraction of the nucleus on the outermost electron, and lesser will be the energy required for the removal of that electron. So the ionization potential will be low. The second factor is the effective nuclear charge. Ionization potential is directly proportional to the effective nuclear charge of the atom. That is, if the effective nuclear charge is high, that is the attraction on the outermost electron is high, the ionization potential, that is the energy required for that removal of the electron, will also be high. The third factor is the screening effect. Ionization potential is inversely proportional to the screening effect in the atom. If screening effect is high, that means the traction of the nucleus on the outermost electron is not as high as it would have been in the absence of the inner electrons due to the internal repulsion between the electrons. The energy required for its removal will be less. That is, ionization potential will be less. The fourth factor is the stable electronic configuration. We know that fully filled orbitals or half-filled orbitals, both of them are extra stable, therefore they require higher energy for the removal of the outermost electron. If we compare fully filled orbitals and half-filled orbitals, the ionization potential of fully filled orbitals will be more than that of half-filled orbitals. Another important factor is the penetration effect. We know that s orbitals are at minimum distance from the nucleus if we are talking about the same energy level. P orbitals have a greater distance, then comes the d orbitals, and f orbitals are furthest from the nucleus. Therefore, the nuclear attraction on the electrons will be highest in s orbital, lesser on p, much lesser on d, and minimum on f orbitals. Therefore, the ionization potential will also be highest for s, and following the same order, least for f orbitals. Oxidation state. Ionization potential is directly proportional to the oxidation state of the atom. So the ionization potential of an element in its second oxidation state will be lesser than the ionization potential of the same element in its third oxidation state. If we look at the values of ionization potentials of various elements in the periodic table, then we find that on moving across a period from left to right, the ionization potential increases with decrease in the size. Similarly, on moving down a group, the ionization potential decreases along with increase in the size. Please have a look at this table in which the ionization potential values of various elements are depicted through the intensity in color. The elements which are lighter in color have low values of ionization potential, whereas those with darker color have high values of ionization potential. So we can see that as we move along the period from left to right, for example, from lithium towards fluorine, we find that the value of ionization potential is constantly increasing. Similarly, as we move down a group, that is from hydrogen, lithium, sodium to cesium, we find that as the size is increasing, the value of ionization potential is decreasing. So we can see that the alkali metals have very low values of ionization potential, whereas inert gases, due to their stable configuration, have very high ionization potential values. Similarly, nitrogen, which is half-filled orbital, again shows very high value of ionization potential. There are some exceptions which are observed in the values of ionization potential. As we said that as we move through a period from left towards right in a periodic table, the ionization potential values generally increase, but we find that the ionization potential value of beryllium is higher than that of boron. It's because of the reason that beryllium has a very stable electronic configuration with fully filled orbitals. Therefore, its ionization potential is higher than expected. Same is the case with nitrogen and oxygen. If we go according to the periodic trend, the oxygen must have ionization potential higher than that of nitrogen, but it is not so. It is because of the reason that nitrogen again has a very stable electronic configuration with half-filled orbitals. Similarly, as we move from aluminium to gallium, that is down a group, the value of ionization potential must decrease, but the ionization potential values for aluminium and gallium are almost equal because of the reason that their sizes are also equal. And as we observed in the table, noble gases have very high values of ionization energies in their respective periods. It is because of the reason that they have very stable electronic configuration with fully filled orbitals, and therefore it is very difficult to remove an electron from their atom. Let us see what trend does the ionization potential follow in the transition elements, that is d block elements. In transition elements, the ionization potential is mainly affected by two factors. One is the effective nuclear charge and the second is the screening effect. It has been found that ionization potential is directly proportional to the effective nuclear charge and inversely proportional to the number of electrons in n-1 d orbital, that is those electrons that cause the screening effect. In the first transition series, as we move from scandium to chromium, that is from the beginning to the middle of the series, the effective nuclear charge dominates over screening effect. So as we are moving from scandium to chromium, the number of protons is increasing, which attract the same electron shells. Therefore, the ionization potential increases. From iron to nickel, the effective nuclear charge and screening effect almost have equal effect. Therefore, the ionization potential remains almost constant. From copper to zinc, the outermost s and d orbitals are half and completely filled, that is, they have a very stable electronic configuration, due to which the increase in ionization potential is low. Manganese and zinc are found to have very high values of ionization potential due to their stable electronic configuration. They have half-filled and full-filled electron orbitals respectively. The value of ionization potential of an element is very useful in describing its chemistry. One of the various properties that can be described is reactivity. Ionization potential is inversely proportional to the reactivity of the species. Most of the reactions that take place involve exchange of electrons. Therefore, those elements which have high value of ionization potential and therefore are unable to part with their outermost valence electron show low reactivity. The second property is the metallic and non-metallic character. Atoms with low ionization potential, which can easily lose electron, are metallic in nature, whereas those with high values of ionization potential are non-metallic in nature. The third property is the reducing capacity. Ionization potential is inversely proportional to the reducing capacity of the element because reducing capacity involves giving up of the electron. Therefore, lithium, which easily gives up its electron because of low value of ionization potential, is the best reductant in first table. Another application of ionization potential is the stability of the oxidation state. If for an element, the difference between the second ionization potential and the first ionization potential is greater than or equal to 16 electron volts, the lower oxidation state is going to be stable. But if the difference is less than or equal to 12 electron volts, the higher oxidation state is stable. For example, for sodium, the first ionization potential is 5.1 electron volts, whereas the second ionization potential is 47.3 electron volts. Now the difference between the two will be 42.2 electron volts. This is definitely much greater than 16 electron volts. Therefore, the lower oxidation state, that is sodium plus, is stable and sodium 2 plus does not exist. Another application is the type of bond formation if the ionization potential is low, that is, the element can easily give off its electron to form ions, ionic bond will be preferred. But if the ionization potential is high, that is, it is not easy for the element to give its electrons and it will prefer sharing the electron, forming the covalent bond to complete its octet. The next application is the basic strength of hydroxides. Ionization potential is inversely proportional to the strength of the hydroxide. We can measure